All right. Well, welcome back, folks. I hope everyone's okay. I haven't seen too many of you folks after school, and so please make sure you come on by and get that help that you may need. Okay. Um, just a quick note: we won't be meeting tomorrow. Tomorrow was a scheduled student holiday for faculty in service, and so we will continue to have that. So we won't meet tomorrow, but we will meet on Monday. So you'll have a 3-day break. Okay, so please get some rest over the weekend, and then we'll meet again on Monday. Okay. All right. With that said, we left off yesterday, and so let's go ahead and get into this. We left off yesterday by just doing a few review problems um, from to help us review the 4 different types of conversions that we have learned it so far in chapter 10. And so remember, we have the 4 types of conversions. Then is a moles. They all involve the moles to particles, moles to mass, moles to volume, and then we were able to use the molar volume in order to do a density to molar mass conversion as well. So keep those in mind. How you will approach solving for these problems, that you'll read the problem, identify and answer 3 basic questions, folks. Identify what they give you to start out with, identify what you are solving for, and then pick the correct conversion factor in order to get that done. So we left off with a few of these practice problems, and I want to continue on with this right now. Okay, and then that way, then if you have any questions about this, you can come on by and get your questions answered. Okay. All right, so we left off with number 10 here. So let's go ahead and let's take a look at number 10 here, and let's work this out. Again, what you want to do is you want to start out with, go ahead and draw a tool here. Okay. What you want to do then is you want to identify what you're given to start out with. Okay. All right, so we are, the problem asks about a density of some gaseous compound. So we have a gas here, so make sure you indicate that we have a gas. That's going to be important in just a moment. Okay, we have a gas that we are dealing with here. We have, this gas contains carbon and oxygen. We have here this number. Okay, so this value right here, and if you look at the units, the density, they already tell you it's density, but this is what we were given, so this is what we are going to start out with. So that's our starting amount right there. So it's the density. So we're given the density to start out with. Also, we have then STP here. Okay, that's going to be important. And so what they want us to solve for, what we want to end up with is the molar mass. So we start with the density. We want to end with the molar mass. So we've answered 3 questions there already. Sorry, 2 questions there already. Since this is a gas at STP, the conversion factor then will be the molar volume. Okay, so that's essentially how you want to go about doing this here. And so let's go ahead and let's solve for this problem then, and let's work it out. Okay, so what we start out with is 1.94, 1.964, and this is grams, and I would suggest you write it out this way. It's grams over liters. And remember, density is always going to be a unit ratio, so it's always going to be some number over 1. So write it out that way. And so that's what we're starting out with. What we're ending up with and what we want to solve for is grams per mole. This is the molar mass. That's going to be grams over moles. Again, this is going to be a unit ratio. That's going to be over 1 mole. So we need to find then what this number is here for the grams. Okay? All right, since this is a gas at STP, then we know that we can use the molar volume, which is 1 mole of a gas. And it doesn't matter what the identity of the gas is, remember, as long as the conditions are at STP, 1 mole of that gas is going to occupy 22.4 liters worth of space. So any gas, and remember, understand this, any gas at STP, and STP then represents a standard temperature and pressure. That standard temperature is going to be 0 degrees Celsius, and the standard pressure is going to be 1 atmosphere. So whenever you have these conditions right here and you have a gas, we can use this molar volume right here. We can use this, this relationship right here to carry out our conversion. Okay, so let's go ahead and plug it into our calculation, our conversion here to get this done. Okay, so if you notice then, we need the 22.4 liters on top and the 1 mole on the bottom. Hopefully you recognize why, because the liter then, unit liter cancels out. We end up with moles on the bottom on both sides of the arrow and grams on top on both sides of the arrow. Okay, so we go ahead then, we know we have the problem set up correctly, plug in our numbers, we end up with an answer then that's going to be 43.99 grams per liter. Okay, and that's going to be your answer for that one. Okay, so good. So I asked you to finish up this problem yesterday. This is the problem that I asked you to do. So please make sure you write those down, this problem down, and on your paper and ready for submission after the discussion is done. Okay. All right. Very good, folks. Let's go ahead then. And let's go ahead and let's go and do another problem really quickly. Okay, let's do, sorry. Let me go ahead and clear this out for you. Okay, let's do these three problems right here. Okay, so take about few minutes. What I'd like you to do, if nothing else, make sure you are able to set up the problems. It gives you a chance to practice the 3 of the 4 types of calculations that we've learned about. Okay, so go ahead, take about 2-3 minutes to set up the problems, and then if you can, go ahead and solve them. Okay, so let's go ahead and get that done. Okay, let's go ahead then, folks, and let's go ahead and work these problems out here. Okay, and I'm going to start out then, and let's work out the first one. Okay, so if you read the first one, then they tell you that at STP, so hopefully you recognize that, what is the volume occupied by 6.7 moles of hydrogen gas? You have a gas at STP. Okay, they give you, so we're starting out with, so the very first problem, okay, we're starting out with then this amount. We're starting out with 6.7 moles of hydrogen gas. Now, again, the identity of the gas doesn't really quite matter here, because we're asked to find the volume, and hopefully you recognize that we're going to be solving for the liters, the volume in liters, because the molar volume is going to be in units of liters. But why is it that we can use this molar volume, which is 1 mole again of hydrogen gas will occupy 22.4 liters of space? Why is it that we can use this particular relationship here? Because they tell us that this is a gas, hydrogen is a gas, okay, and the gas is at STP. So once we have that recognized and we've identified that, we can use a molar volume. Okay. All right. So with that said, then we're going to plug in the molar volume. Will multiply by the molar volume, which means then we'll have 22.4 liters on top. Okay, and 1 mole on the bottom. That allows us to cancel out that unit. Liters on top on both sides, and we get our answer then as being 150 liters. Yes. And that's our answer. So this is an example. This is an example of the calculation that we did. That was let me go ahead and write this down. This was the moles to volume conversion. So this is a moles to volume conversion. And again, what we would use here for the moles to volume conversion is the molar volume. Okay, so that's the first type of, so that's one of the conversions that we've done so far. Okay, let's go ahead, let's take a look at the second one. Problem number 2. Right, so problem number 2, they're asking us about moles, and then they give us the masses of each one of these substances here. Okay, so let's go ahead. What we have here for the very first one then is we are given mass 15.5 grams of silicon dioxide. That's what we're starting with, and they're asking us to find the moles of equivalent to that amount of silicon dioxide. This is a mass to moles conversion, folks. And so with that said, then the conversion factor that we're going to use is the molar mass, which is what is the mass equivalent, the mass in 1 mole of this particular compound. Okay, and how do we get this? Well, we add together all of the masses that we have of all the atoms there. So we have 1 silicon atom and 2 oxygen atoms. If we add those masses together, we're going to get a mass then of 60 grams of silicon dioxide. Okay, where did we get this number? Well, we find the molar mass of this atom here of silicon. We get that from the periodic table. We find the molar mass of this atom here, again, from the periodic table, and we add them all together. So silicon and 2 oxygens, and then that's where you get your 60 grams of silicon dioxide for every 1 mole. So this is what we refer to as the molar mass, remember. So this relationship here holds only for silicon dioxide. Okay, all right, so with that said then, we can plug it in. Let's go ahead and plug it in and work out our answer so that we have then 1 mole of silicon dioxide over 60 grams of silicon dioxide. And we plug that in, the unit grams here cancels out. Okay, we plug that in, we get our answer then as 0.258 moles of silicon dioxide. Okay, all right. So this is what's called the molar mass, folks. So this is the molar mass. Okay, and for the molar mass, make sure you remember this. The molar mass of an element, you get it straight from the periodic table. The molar mass of a compound, you actually have to calculate for. You just add up all the atoms that make up that particular compound. Okay. All right, so that means that if you take a look at the second problem, it is also a mass to moles conversion. Okay, so this time we have 79.3 grams. This time the substance is chlorine, diatomic chlorine, and we're going to solve then for the moles of chlorine. And so we need the molar mass of chlorine, which is 1 mole of chlorine, and it's equivalent in terms of mass. And we get that there, that would be 71 grams. Just again, add together 2 chlorine atoms. Okay? That's the molar mass of chlorine. So we're going to plug that in, okay, as 1 mole. So the way that we set it up is the exact same. It's just going to be a different molar mass, 71 grams of chlorine. Okay? That allows us to cancel that unit out. Okay, and so therefore we end up with an answer then as 1.11 moles of chlorine. Okay, and so what we have here is a second type of conversion that we're going to be doing, that we've done already, and this is going to be the moles to mass conversion. So this is an example of a moles to mass conversion. Okay, so make sure you review that one if you don't remember this one. Okay, so let's go ahead and take a look at the last problem. Sorry, this is not quite out as well as I wanted to. Okay, so the last one here. All right, so we have then, they want us to find, in this case, the mass, and they give us the moles of these 2 substances here. Okay, so this is going to be the reverse. 3 is a moles to mass conversion. If in number 2 we start out with mass and we were solving for moles, in number 3 we are starting out with moles and we were finding the masses. Okay, so let's go and write this down. So we start out with 1.50 moles. So we're going to use the molar mass for each one of these as well, of pentane, which is C5H12. All right. And this time we're going to find the mass equivalent to that many moles, so C5H12. Okay, so 5 carbon atoms, 12. So I'll leave it up to you to calculate for that, right, folks? Okay. Practice that. But 5 carbon atoms and 12 hydrogen atoms together will be 72 grams per mole. We're going to plug it in, so it's going to be 72 grams of C5H12 over 1 mole of C5H12. That allows us to cancel out the moles here. We plug in our answer, then we get our answer. Then is be 108 grams of C5H12. So this is also a mass to mole. This number 3 is exactly like what we did in number 2, but this time though we're starting out with moles and we're solving for mass. Okay, so make sure you keep that in mind. That's where we get this number from. This is the molar mass of pentane, C5H12. Okay. All right, let's do the last one then. We have 0.780 moles. So we start out with 0.780 moles of calcium cyanide, CaCN2. We're going to find the grams of CaCN2. Right, and so we need the molar mass, and we're going to multiply by the molar mass of calcium cyanide, which is going to be 92 grams. Okay, so let's go ahead and plug that in. 92 grams CaCN2, over 1 mole of CaCN2. All right, so you plug that in, the unit of mole cancels out here, and we plug in, we get our final answer then, 71.8 grams CaCN2. Okay. So with that said, this allowed us to practice 2 of the 4 types of conversions that we did in this chapter so far. Okay, so make sure you practice this here, folks, and then come by and see me. I'll be available after school today, 3:15 to 4:15, to get extra help with this. Okay. All right. So let's go ahead then and let's continue on then. Okay, so we're going to start talking about then what's called this percent composition. And I'll we'll finish up with this today. And the discussion of this percent composition is going to lead us then into and allow us then to determine what we refer to as these empirical formulas. From that, we can get the molecular formulas or the actual formulas. The term molecular here is used generically to describe just the actual formulas for a particular compound. Okay? Molecular, so we will solve for the formulas for the ionic compounds as well as the molecular compounds themselves. So I'll identify what these empirical formulas are, but like I said, it's that composition here that we will use to get this empirical formula. From the empirical formula, then we can derive the molecular formulas. And those molecular formulas, folks, are the formulas that we have been working with. Okay? All right, so with that said then, what is percent composition? Okay? Well, all compounds are made up of a certain amount of atoms in a fairly set ratio. We learned about that back in chapter 4 when we talked about Dalton's theory. Okay, so with that said, then what you need to make sure you keep in mind then, and let me go ahead and change this here really quickly. Okay, that this idea of percent composition, what we have here then is the amount of a set of elements in a compound itself. It's going to be the relative amounts. And just like what we said with, and hopefully you remember this, that when we talked about percentages, okay, the percentage here, a percentage is always a part. It's a ratio of some part over whole. We learned this in math. Some part over whole times 100. We need to identify this part here to find the percent composition, okay? And then we'll multiply it by 100. And so the part of the whole here then is going to be the amount of a particular element in the total compound itself, and we'll define that in just a moment. Okay, so the composition here, when we talked about this in terms of chemistry, this percentage then is going to be then the element, total amount of element, total element, okay, over the total compound. And how we get these totals, I'll talk about in just a moment, times 100. There's your part over the whole, okay? And so that's what we will be focusing on when we do these problems here, okay? All right, so let's take a look at an example. Let me clear this out first. Let's take a look at an example here. This is the compound here. This is potassium chromate. Potassium chromate is made up of potassium, chromium, and oxygen. These are the elements here. When we break this down, so we run a decomposition reaction. And we compare the amounts of each one of these elements here to the total amount of the compound itself. We find then that it ends up being that we have about 40% of this compound is made up of potassium, about 27% is chromium, and about 33% is oxygen. Okay, so these are the percentages here. We can obtain these percentages by using masses or any measure that we can use to compare the amounts of each total amount of the element in the compound itself. Okay, so if you take potassium chromate, regardless of how big or how small that the sample is, the amount is, these percentages will always be the same. Okay, and if you notice here, if you add these up, all these three percentages will add up to be 100%. Okay. All right. So how can we obtain these percentages here? Where do we get the numbers that we use to obtain these percentages? Well, a couple ways. We can obtain the percentages using the masses here. The masses of each one of those elements in a particular compound. Now understand this, how we go about doing this, and this is where what we did back in chapter 11 is going to help us. We can run a decomposition reaction. Okay, so if we run a decomposition reaction, composition reaction, we can take then a particular compound. Remember we did this. We can take a particular compound, especially if it's diatomic, okay, binary, and break it up into its elements. Okay, and so if we have a certain mass here, let's say we had 100 grams here that we started out with, okay, and then we ended up with when we break it down, we end up with 60 grams of A and 40 grams of B, and that has to be the case. This is the amount of A, the element A, that was originally in this compound. This is the amount of B that was originally in that compound. And so therefore, we can obtain the percent composition by comparing these masses to the total mass here, these masses to the total mass. And that's what we mean by obtaining the masses experimentally. So that's one way then that we can obtain the percent composition. Okay, all right. So let's take a look at an example then. Okay, so once we have these masses here, we take the mass of each one of these elements. So let's go ahead and do that. We take the masses of each one of those elements, okay, and then we divide it by the whole number. So let's go ahead and let's take these numbers here really quickly. Okay, and so let's say then the percent of A in AB is going to be the mass of A over the mass, total mass of the compound, AB. So plugging that in, and we're going to multiply it by 100. Okay, so plugging those values in, let's go ahead and take a look at this. So the percentage of A then is going to be 60 grams, because that's what we had when we decomposed it, over 100 grams total of AB, okay, times 100. Okay, and so if you do that, then you're going to recognize then that the percentage of A then is going to be 60%. And that's how, folks, we get the percentage percent composition. Doing the same thing for B then. Okay, so the percent of B is going to be the mass of B over the total mass of the compound, which is AB, which is what we started out with, times 100. So which means then the percent of B then is going to be 40%. So I'm sorry, 40 grams. That's the amount of B that we have when we decomposed it. All over 100 grams is what we started out with of AB times 100. And so we end up here with 40%, which is the percentage of B. So that's how easily we can go ahead and get these percentages, okay? And so make sure you keep that in mind as we go about doing this, okay? All right, let's go ahead then. And I'm running a little bit over time here, but I just want to make sure I give you a chance to practice doing this a little bit, okay? So let's go ahead then. I'm going to clear up this screen here. Hopefully you got that, folks. And let's take a look at an example problem here, okay? All right, so let's go ahead. And let's work this problem out, okay? So we have here, so let's take a look at the compound. So whatever this compound is, it's made up of magnesium and oxygen. Okay, so whatever the compound is, it's made up of magnesium and oxygen. Okay, so that's our total compound. We were told then that the total here is going to be 13.60 grams. Okay, so that's the total amount. That's our total. Okay. Okay. And then we're told then that when we decompose this, so let's imagine this is the reaction we're looking at, magnesium oxide breaking down into magnesium and oxygen. Okay, so that's the decomposition reaction that we're going to follow. Okay, and so we were told then that we start out with 13.60 grams of magnesium oxide, and when we break this down, then we are told then we obtain 5.40 grams of oxygen. Okay, all right. So how then would we obtain the amount of magnesium, the mass of magnesium that actually forms when we decompose magnesium oxide? Well, folks, if this is the total and this is how much oxygen we have, since this is a binary compound, we can subtract this number from the total. We end up with 8.20 grams of magnesium, okay? All right, I hope everyone's okay with that. All right, so therefore, what we can do then is to get the percent of magnesium. Let's do the percent of magnesium. That is how much magnesium, the percentage of magnesium in magnesium oxide. We're going to take the mass of magnesium, that element, over the total mass of the compound times 100. Okay, so let's go ahead and plug in our numbers. The mass of magnesium is given to us on the top there, okay, which is going to be 8.20 grams. That's the mass of magnesium over the total mass of 13.60 grams, and that's the mass of magnesium oxide times 100. You plug that in, you'll get your value then of 60%. Rounded to the whole nearest whole number. So that, folks, is the percentage of magnesium. Okay. The percentage of oxygen then, doing it the same way. The percentage of oxygen then is going to be the mass. The mass of oxygen over the total mass of the compound times 100. Let's go and plug in our numbers here. The mass of oxygen is given to us is 5.40 grams of oxygen, of the element oxygen in magnesium oxide, over the total mass of 13.60 grams of magnesium oxide times 100. And then we get our answer then rounded to the nearest whole number as 40%. Okay. And so those are our percentages right there. Okay. All right, so calculating for these percentages are going to be fairly straightforward and fairly simple. What I would like you to do then, and to finish out here, what I'd like you to do, I want you to take a look at number 27. Okay, so let me clear this out for you. Okay. Take a look at number 27. I would like you to work this problem out on your paper, and then you'll submit it. And then what I'll do on Monday is I'll work out this problem for you. Okay, so finish out with number 27, submit your work, and then we'll pick up with this problem on Monday. Okay. All right, very good, folks. Have a good weekend, and I will hopefully see you either after school today, or I will see you on Monday. Okay. Have a good weekend.